So in this set of slides, we're continuing the examples of entropy in the second law. So in this example, we've got entropy change during heating and cooling. So we've got 200 grams of water at 95 degrees Celsius added to a 150 gram glass cup at 20 degrees Celsius. The two objects come to equilibrium at a temperature of 85.8 degrees Celsius. Determine the entropy change of the universe. Okay, so we've got, in this diagram here, we've got heat flowing from the hot thing to the initially hotter thing to the initially colder thing. So I'm assuming T1 is bigger than T2 here. And so we've got the heat going from the object 1 into the object 2, and then the temperatures will change and it will come to equilibrium. So to calculate the entropy change of the universe, we need to calculate the entropy change of object 1 plus the entropy change of object 2, right? So entropy change of the universe is adding up all of the entropy changes in the problem. All right, so first let's work on the entropy change of object 1. As usual, we start by writing the schematic formula dq over T. So remember, what is this? This is the entropy change of object 1. That's the heat added to object 1. And that's the temperature at which it's added. Okay, now in previous example, T was constant, so I could pull it outside. But in this case, I can't pull T outside. T is not constant because as heat flows out of object 1, its temperature changes. Okay, so I can't pull T outside. I have to leave it inside the integral. So my strategy then is, because I have heat leaving, temperature changing, I use dq is m1 specific heat of object 1 times dt. So this is the same as q is mc delta t, which you guys are familiar with, right? But just in infinitesimal form. So I'm substituting that in to that integral, and I get delta S1 is equal to integral m1 c1 dt over t. Now the integration variable here is dt, so my integral goes from my initial temperature to my final temperature for object 1. So my initial temperature is T1, my final temperature is Tf. Okay, now the mass of object 1 and the specific heat of object 1, in this case, is constant, so I can pull those out. So pull out these constants. They can come outside of the integral. So I get m1 c1 integral T1 to Tf dt over t. And that is a natural log. Tf minus natural log, of T1 and by the rules of logs you can combine this like this, Tf over T1. Okay, so that's the entropy change of object 1. The entropy change of object 2 is done almost exactly the same. It's just that I start at T2 and go to Tf. So I will just write that out really quickly. And there it is. So I've got delta S2 is equal to this, and delta S1 is equal to this. So the formulas look exactly the same, just that everywhere I had a 1, I have a 2 now. So now let's combine everything together and determine the entropy change of the universe. So I just collected the information from the previous slide. Notice that delta S1 is going to be less than 0, and delta S2 is going to be bigger than 0. You can tell this because remember that TF is going to be smaller than T1 because heat is flowing out of object 1 until it reaches TF. So that means that the natural log of TF over T1 is going to be less than 0 because the natural log of a number which is below 1 is going to be negative. And then you can go through the same argument for object 2. TF is bigger than T2, so the object or the term inside of the natural log here is bigger than 1, and so you end up with a positive number. So we have the same situation that we had in the previous example. One of these entropy changes is positive, one of the entropy changes is negative, because heat is going out of one thing and into the other thing. So the heat that goes out of object 1 loses entropy. Object 2 has heat coming in, so object 2 gains entropy. It's not so obvious in this case which one is going to win, so the best thing to do is plug in the numbers and see whether the entropy change of the universe is positive or negative. So let me do that. I'll spare you the time of me writing out by plugging in the numbers here, but let me plug in the numbers very quickly. So there are all the numbers. So I plugged in the mass of the water, specific heat of water, and those temperatures converted to Kelvin. So make sure you remember to convert to Kelvin. We're dealing with absolute temperature scales here. And then mass of the cup, specific heat of the cup. Okay. So what do we have? When you plug in the numbers, for the water we get minus 21.19 joules per Kelvin. And then for the cup, we get plus 25.51 joules per Kelvin. One is positive, one is negative. This is delta S for the water, and this is delta S for the cup. But you can see that the positive one is bigger than the negative one is. So as before, we end up with a positive number. Adding those two things together, I get 4.32 joules per Kelvin. Notice again, delta S universe is bigger than 0 here. And also notice that this is an irreversible process. We're seeing heat being dumped from the hot thing into the cold thing and reaching a final temperature. If you took a video of that, you would never see the reverse thing happen, where they start at the same temperature and then suddenly separate, where one of them becomes hotter and one becomes colder. So irreversible process, entropy change of the universe is positive. All right, let's do one more example. In this third example, I want to think about the entropy change of the universe when an engine performs a cycle. So this example is a Carnot engine working between two reservoirs, TH and TC, completes one cycle. Determine the entropy change of the universe. So on the left here, we've got the diagram of the engine. And remember that Q in is heat coming out of the hot reservoir into the engine. The engine performs some work and then dumps some heat Q out into the cold reservoir. On the right, we have the PV diagram for that situation. So unlike the previous examples, I have three objects which could undergo an entropy change. I have the engine itself, I have the hot reservoir, and I have the cold reservoir. So if I want to calculate the entropy change of the universe, I need to add up delta S for the gas inside the engine. So we're assuming it's an ideal gas engine, plus delta S for the hot reservoir, plus delta S for the cold reservoir. So I need to calculate all three of those things and then add them up in order to calculate delta S for the universe. Okay, so the first one is easy. delta S for the gas. This is a cycle where the gas goes from point A to point B to point C to point D back to point A. So it's S final minus S initial, but because the initial and the final are the same, it's a cycle, it's going to be equal to 0, right? So this is a cyclical process. So initial and final states are the same. Just like that. Okay. So actually, no matter what kind of engine I have, even if it's not a Carnot engine, any kind of process which starts and ends at the same point will have delta S equal to 0. That's because S is a state variable. So as long as I start and end at the same place, delta S will be 0. Okay, now let's think about the harder concept of what's going on with those reservoirs, TH and TC. Okay, let's think about the entropy change of the hot reservoir, delta S, hot res. We'll start as usual, right? dq divided by T. And as always, the entropy change of something is the heat added to that thing. So in this case, it's the heat added to the hot reservoir, because I'm looking at the entropy change of the hot reservoir, divided by the temperature at which the heat was added. Now in this case, because it's a reservoir, this temperature never changes. So it's just going to be TH, right? And that doesn't change. The reservoir is huge. It gives up a little bit of heat. Its temperature doesn't change. And so now I'm in paradise. I can put this T outside because it's a constant. So I have here 1 over TH integral dq. And this is the integral of dq. I don't have to do anything fancy. It's just going to be q. Let me call it hot res divided by TH. So that is the total heat added to the hot reservoir divided by TH. But of course, no heat is being added to the hot reservoir, right? Heat is being removed from the hot reservoir, and we call that heat Qin. Qin is a positive number. So because heat is coming out of the hot reservoir, I'm going to write here minus Qin divided by TH. So Qin is a positive number. That's the amount of heat that's being added to the gas. By conservation of energy, that's the amount of heat coming out of the hot reservoir. So the heat coming out of the hot reservoir is minus Qin. Qin is a positive number. That minus sign tells me that heat's coming out of the hot reservoir. The steps for the cold reservoir are basically the same. It's just everywhere I have TH, I need to have TC. And the entropy change will be positive because heat is going into the cold reservoir. So let me put those details in very quickly. So I just wrote the same thing again, but just instead of Q in, I have Q out. Instead of TH, whoops, I should have TC. So this should be TC. Again, the minus sign is confusing. So let me remind you that Q out up here is a negative number. Q out is a negative number because it's going out of the gas. Okay? Q in is a positive number. Now, if I want the entropy change of the cold reservoir, I'm having heat added to the cold reservoir. So the entropy change of the cold reservoir should be positive. So I have to add an extra minus sign. So Q out is negative. But then there's an extra minus sign so that the total entropy change is positive. Okay? So now we have everything. We just have to collect everything together. And then we can write down the entropy change of the universe. So I just collected all the things from the previous slide. So the change in entropy of the universe is the change in entropy of the hot reservoir, which we said was Qin minus Qin over Th, and the change in entropy of the cold reservoir, which was minus Q out over Tc. And I can write that as shown here. Okay, now, is this a positive number or a negative number or zero? It's a little bit hard to tell because, like I say, the sign conventions are a little tricky. But remember that the efficiency for any engine is 1 plus Q out over Q in. This is any engine. But then we also worked out that for a Carnot engine, it's 1 minus T cold over T hot. This is Carnot. By setting those things equal, because in this case we have a Carnot engine, and a Carnot engine is of course any engine, I can set those two things equal to each other. So eta equals eta Carnot, because it's a Carnot engine. And I get 1 plus Q out over Q in is equal to 1 minus Tc over Th. The ones cancel. And you can rewrite this as Q out over Tc is equal to minus Q in over Th, which we've seen before, but I'm just rederiving it for you here. Which means that this whole thing for the entropy change in the universe is 0, because I have exactly that combination. Q out over Tc here is equal to minus Q in over Th here, so when I add those two together I get 0. So in this case, the entropy change of the universe is 0. How do I understand that? All the examples we did previously, we saw the entropy change of the universe was positive. But remember what's special about a Carnot engine. A Carnot engine is a reversible process. So the Carnot engine I could run forwards or backwards. And that's the thing that makes it special, that the entropy change of the universe is 0. So we've done 3 examples now, and we saw that for the irreversible processes, delta S for the universe was always positive, and for the reversible process, delta S for the universe is equal to 0. So now we're ready to formalize a final formulation, a connection between entropy and the second law of thermodynamics and reversibility.